In August 2009, during track and field world championships in Berlin, Jamaican Usain Bolt ran 100 meters in 9.58 seconds. This is the fastest time recorded in the history of mankind. He broke his previous record by a staggering 11 hundredths of a second. This is the highest margin since the beginning of automatic time measurements. Perhaps you're wondering how much faster Usain Bolt runs as the best athletes of the past, and what difference did advances in sports science and medicine, in state-of-the-art running shoes and nanotech clothes, what difference did they make? The earliest recorded 100-meter run dates back to 1891, and the time, 10.8 seconds. So it took us over 100 years, billions of dollars, and decades of research to run 100 meters 1.2 seconds, or roughly 12% faster. Improving performance can be hard, and we as compiler engineers understand it quite well. Improving performance of already optimized binary is even harder. And today, I will talk about the modifications that can be done to already compiled and linked binary. There are multiple applications to this technology, but my primary focus will be on improving performance on top of compiler and linker. The gains I'll be talking about, they can appear small, but when applied to an application that runs, say, in multiple data centers, these gains can result in massive savings of CPU time and power. Without further ado, I present you a different kind of bolt. It's a binary optimization and layout tool. The project was started in August 2015, and it is barely 7 months old. And at the same time, it already runs in a limited production. This means that some of the requests that are going to Facebook are actually executed on the binary that is optimized by Bolt. And this binary is a 64-bit x64 architecture. All this is possible thanks to the great set of libraries and the framework created by an awesome LLVM community. So today I'll talk about why do we need a binary optimizer, and why LLVM is such a great choice to build a binary optimizer. What challenges are we facing while building a binary optimizer, and what approaches could be taken for the implementation. I will share in more details the results that we've achieved so far, and conclude with the plans for the future. So why do we need a binary optimizer? In short, we want to extract every single bit of performance of the binary. After compiler has run and linker has run, we want every single bit. And we use a feedback profile that was generated in production. And the feedback profile actually tells you a lot about the binary itself. And it's much easier to use this profile to optimize the binary. It's much easier than to link the information that you gained on instructions of x86 and try to link this information to source code or to higher level IR. You also don't need the source code to do binary optimization. And this is the case when you have libraries, perhaps from third party, where you don't have control or don't have access to the source code. Binary optimizer also has a whole program view. I put it in quotes because in reality, your application does not consist of one binary. It can consist of one binary in several shared libraries. But in our practice, if you want to gain the maximum performance, you try to put as much of the code in a single binary. There are also a set of optimizations that I'll briefly cover at the end of the talk that can only be applied to the binary itself. They cannot be done at the link time. They cannot be done at the compile time. This is not the first binary optimizer. I listed a few on this slide, and perhaps I miss a lot more binary optimizers. Probably you worked with some of them. I wouldn't be surprised if you implemented some of the binary optimizers. Unfortunately, most of these, if not all, they are not open source. And some of them you cannot actually even have access to the executable. Some of them, like Sun Studio or Oracle Studio Binary Optimizer, which I worked in the past, it requires a special kind of compiler that inserts annotation into the code to facilitate disassembling of the binary. Here's the user model for the binary optimizer, how you're supposed to use it and how we use Bolt at Facebook. So I'm giving an example of HHVM running in production. You run the Linux perf tool, you record some events, but most importantly, you record the branch information. Intel CPUs, they have a wonderful feature called last branch record, where you can obtain, for every event, the history of last 16 branches taken. And this allows you to annotate the control flow graph with precise, not precise, but approximate edge information, edge frequency information. Once you have the perf data, you use the binary that you just ran, and you convert the data to a different format. You need this step because you don't want to use the exact same binary all the time. You want to reuse this data with the recompiled binary. Perhaps you modify the source code. And this step allows you to do this. So it converts the perf data into the data format that is more resilient to changes in the input binary. After this step, you actually do the binary optimization. And this model is pretty simple. You just pass it the profile data and the input binary. It produces the output. The speed that it runs with is actually quite amazing. I think originally it took us 2 minutes to process over 100 megabytes of source code. And I'll give you an example. Our linking step right now takes about 20 minutes. And it's using gold linker. The only problem is that we're using the linker script. And the usage of the linker script slows down the linker considerably. Why LLVM is such a great choice to build a binary optimizer? Well, it has disassembly, because you want to convert a sequence of bytes into a sequence of instructions, and it has an assembly too. There are many other disassemblies and assemblies. What makes LLVM quite unique is that both assembly and disassembly share the same representation. You don't need to convert one from to another. And even more importantly, we have elves, dwarfs, and orcs. Orc is a recently, let's say, added feature. It's a kind of replacement for MCJIT. It's called, I think, on-request compilation. But in fact, what it is, it's a layered approach to code generation. So you can generate code for binary optimizer or for execution in memory for just-in-time compilation. For us, it was a perfect fit to use for binary optimization. Since our input format is ELF, it was important to be able to process sections and segments and to output with slight modifications. So this is where ELF comes from. And dwarf, I will talk in a little more detail about this. It's basically a debugging information format which we need to update. And LLVM has, again, it's absolutely amazing, the set of utilities to work with dwarf format. This is a quick overview of the binary optimizer phases. First, you start with the code discovery, and you continue with disassembly. Sometimes these phases are combined into one, but for us, it was much simpler to do this in separate steps. Then you build a control flow graph since you want to optimize your functions and your code. Once you've done this, you perform the set of optimizations, and sometimes you add with more code than you started this, so you need to put it somewhere in the binary. So there's an additional step to discover the storage in the input binary. And finally, you do code emission and file updates. Discovery process that we use relies on the symbol table information. This means the input binary has to be unstripped of the symbol information. We don't need debug information, but we need symbols. So every function will have its boundaries indicated in the symbol table. Same for data, but we don't do data optimizations, at least not at the time. One exception, functions written in assembly. Sometimes people who write code in assembly, they just don't update the function attribute. There's another source for finding boundaries, and on x64ELF, it's EHFrame. This is an unwind information, and it includes the boundaries for all the functions in the boundary. Again, sometimes third-party code or assembly code will omit this information. There's generally no solution to finding boundaries in this, or function boundaries in the set of bytes. Once you try to solve the general case, you realize you run into something like a halting problem. But we don't need to optimize everything. We try to optimize only the parts of the binary that we know we understand. What can really facilitate binary optimization is relocations from the linker. The linker has an ability to preserve relocations. Even after it processed everything, it can maintain the sections. There is a special option called emit relocs or -q, but we cannot use it. With Gold, we currently use 3 features, each of which is incompatible with this option. The first option is identical code folding. We need it for performance. The second option is garbage collection for sections, where we don't want to include in the binary functions or sections that are actually not referenced. And the third, most important for us, which is the linker script. It specifies the function order, the optimal layout for performance. It currently gives us about, I'd say, 5% of performance, so we cannot live without it. So we cannot rely on relocations, not at this time. How do we do disassembly? It's quite simple. You give function boundaries, and LLVM library will produce you the set of MC inserts for the sequence. However, since we want to move this code or to modify it, we need to recreate relocations. If there was a jump instruction or a branch instruction, the destination can change, so we recreate relocations. We do a similar step for data. On x64, most of static data references are RIP relative. Once you move an instruction that addresses some static data, the address of the data changes too. So again, simple solution, we just create relocations. Once we have disassembled the binary, we understand, and we sure we understand every instruction in it, we build the control flow graph. We don't at the moment raise the representation for machines to machine instruction. If we were able to easily do it, perhaps we can utilize the existing machine function of LLVM. But this step, the step of raising for machines to machine instruction, it's feasible, but will require some time for implementation. So it's still possible we may do it in the future. Right now, we don't. So we build our own control flow graph, we build our own function which uses mcinst as a set of instructions. We considered multiple approaches to process the binary. You can start with small binaries, make sure you understand it. Let's say you take some simple program from spec 2006, and you process function by function, and then you rewrite the whole thing. Our primary objective was to optimize HHVM. HHVM is huge. It's millions of lines of code and third-party libraries. So this approach will take some time. Instead, we chose we'll optimize only the functions that we understand. Right now, this is approximately 90% of all functions in the binary. So how can we optimize them? We do it in place. We don't move functions because we don't know the rest of the functions. We cannot move them. So we stick to the original function body. It doesn't always work. As I mentioned, the code that you generate can be larger than the code that you started with. So it wouldn't fit into our original function body. So what do? We move the cold code to a different section. We identify cold code, move it further away. And it's actually performance mean too. The current set of optimizations is very simple, but it produces good results. So we start with just basic block reordering. We're using the slightly modified Pettis-Hansen algorithm. And based on the profile, we try to minimize the number of branches taken, which improves the branch predictor mechanism. We try to minimize iCache and ITLB misses. As I mentioned, the data that we use to guide this optimization is gathered in production, and it uses LBRs. The optimization that we do is performed on top of the linker script. We have a special step that optimizes the function order in the binary. So functions are already put in the best possible sequence. And we currently don't have to do it in the binary optimizer, but something to consider for the future. Once we have all the code and the representation after optimizations in the memory, we try to find a space in the binary, and this is quite interesting. The problem is similar to what hackers are facing. When they want to introduce new behavior to your binary, they need to inject the code there. And there are several tricks you can do. On ELF, you can try to extend the existing program header table to add the new segment of execution. Unfortunately, doing it in place requires shifting of other sections, and you don't always have enough padding to do this. We actually relocate the program header table, and it has some challenges because the link to the program header table is maintained in ELF header, and this link is an offset. But this offset is different depending if the loader looks in the file or in the memory. Since we're relocating program header into a different segment, the offset in memory will be very different from offset in the file. So we have to do tricks for this offset to be the same. Once we wrote the code and updated the program header table, we also do update of the section header table. We actually don't have to do this because sections are invisible to runtime loader. all runtime loader cares about are segments and dynamic segment or section. But we still do this. It will be useful for further analysis of the binary by engineers. I hope that it will also help the strip command to work on the binary optimized binary. Unfortunately, it didn't. If you currently run the strip command, it will try to do the new layout for the binary based on the sections there. And it tries to extend the program header table. It doesn't know the trick how to move it to a different segment. And when it does so, it overwrites the rest of the sections. And it corrupts the binary. It doesn't give up. It gives you a warning that I'm going to corrupt the binary. So cannot use strip with this approach. Still looking on workarounds. Well, one solution is replacing the existing program header tables, program header table entries. So once we did all this, I think we were quite excited to do the first run for HHVM. We have a set of tests. As I mentioned, the run of the binary optimizer itself was quite fast, just under 2 minutes. And once we did it, about 2/3 of the test failed. And actually, we did all the right modifications to the code. Everything was correct. But there was one thing, major thing that we were missing. I don't know if you can guess what it is, but it's, since our binary is written in C and C++, you need to update exception header, exception tables. And this proved to be a lot of work. We need to update 3 sections for this based on modifications to the code itself. We need to update the unwind information in HHVM, which maintains CFI instructions. We rely on the heavy use of remember state and restore state. We also had to modify HHVM header, which is a quick reference for runtime libraries to access HHVM. And then, of course, the exception tables themselves with call sites, the GCC accept table. Once we did this, we were ready to do the benchmarking. The test passed. Surprisingly, didn't take us that long. I think we were about 4 or 5 months into the project when this happened, so we were ready for benchmarking. And benchmark that we use is not spec. We are not actually interested in spec. Spec is quite small compared to the binaries that we run at Facebook. And we didn't need a publication, so we just did HHVM. And there are a different set of binaries in my pipeline that are way more interesting than spec. So what is HHVM? HHVM is a PHP JIT that we use at Facebook. It executes JITed code, and it also executes the runtime. And the split between runtime and JITed code is, I don't know exact numbers. I think it might be 70% in runtime, 30% in JIT, something like that. So, and we only optimize in runtime, so we are not optimizing JIT. And JITed code already has a similar set of optimizations. It has a split code, hot and cold code. HHVM source code is available on GitHub. It's used not just by Facebook. It is used by Wikimedia and several other companies. But at Facebook, we also, in addition to open source, we have a set of linked in third-party components. The resulting binary is quite large. It has 100 megabytes of code. Well, it varies, but sometimes it's 150. But the binary itself is, with debug information, about 4 gigabytes. I want to tell you a little more about the input binary because it's heavily optimized. It has hot paths marked with built-in expect. It has some of the functions actually handwritten in assembly. The flags are carefully tuned for inlining and otherwise. As I mentioned, we use linker script. We use huge pages for code, for JIT code, and for code in the binary. And right now, we optimize about 90% of the functions. And here are the results. So we improve iCache miss rate by about 6.5%, and similar for the branch misses. Notice that ITLB is not actually improved. And I suspect it's mostly because we don't run into ITLB issues since we use huge pages for hot code. There is a little improvement in instructions, probably because our hot paths have less branches now. And a tiny improvement for last level cache. The CPU time improvement is 3.5%, which again may not appear as much, but it's actually quite, for the binary that's already optimized, it's quite a good achievement. What else do we have to do with the binary? We have to update debug information because we need to do debugging even in production. There are a set of sections that we need to update. Some of them have to be rewritten almost from scratch. LLVM gives a lot of libraries to do this, and it's currently a work in progress. We plan to complete it in, I would say, April. Of course, once we start doing more optimizations, such as inlining, updating debug information will be more challenging and require more work. What are the current limitations for the binary optimizer? There are, I would say, two major classes of limitations. Some of them are more fundamental, and others are just limitations of our implementation. So you need a well-formed C++ code. If you have a call into the middle of the function, or if you have a call, let's say, to some function plus an offset, it's not a portable code. And it's very hard for binary optimizer to understand, especially when it doesn't have relocations from linker. There is a self-modifying code. It relies on some previous layout of the code, some previous instructions. We sometimes can detect it and just leave it in place without touching the functions. But in general case, it may be undetectable. The self-validating code that checks, let's say, the checksum of the given functions. Again, since we are doing optimizations, unless we understand the algorithm that is being used, we cannot do much. There are also a set of limitations that we haven't implemented yet. We haven't implemented support for switch tables. It's not that difficult. We just didn't have time for this yet. I know it's possible. I've done it before, so it's just a question of time. And another thing is multiple entry functions. These typically come from assembler. Again, we just don't see that many of them. It wasn't the highest priority. What are our plans for future optimizations? Of course, we plan to do 100% coverage, and we plan to do more optimizations, such as inlining. We can do devirtualization with LBRs. We have a lot of data to perform it quite well. We can do a conditional tail call optimization. This is basically when you replace, when you have a tail call and you have a conditional jump to a tail call, you can have a conditional jump directly to the function. Unfortunately, it doesn't always work as an optimization. Could be a pessimization too, depending on the layout of the functions. Since we work at the binary level, we know exactly the layout, and we know how the branch predictor works. So sometimes we can do it when we know it's optimization and skip it other times when it's pessimization. We can also break some ABI. considerations. For example, if you know and we can analyze the function call chain, we can remove the redundant register fields and reloads. And something for the future, we can do data reordering to improve data cache performance. What I would really like to do is to use linker relocations to do the complete processing for the binary. There are 3 major stoppers at the moment. We need to implement the same set of optimizations that linker does. And this is identical code folding, unreachable or dead code, and we should also do function reordering. I believe, at least for some of these optimizations, we can do better than the linker. Once we have 100% coverage, of course, we can move code and combine basic blocks from different functions together. And what will be really interesting for the future, try to use the same techniques and integrate them in some sort of runtime engine and create a system where you can do performance monitoring at the runtime and adjustment to the binary in time. So it's kind of JIT for C and C++. I think this concludes my talk. I can do the comparison to AutoFDO and LTO, but okay, it seems like we have 5 minutes, and it's quite interesting. So our goal is not to replace AutoFDO or LTO. We want to complement the current set of compiler and link time optimizations. In practice, we had mixed results with AutoFDO. I've seen where AutoFDO did pessimization to the binary. It also didn't work for us on HHVM, at least not with the version of the compiler we are using. So I cannot say that we add that much on top of AutoFDO right now. And here's an example where you have information at the binary level about the execution count in the function. Let's say you know that functions bar and bars were executed exactly 1,000 times. And both of these functions call function foo, which has a condition, and there's a statement of the both sides of if-else. And of course, if you just use the propagation of the counts, you'll see that each of these statements or each of these macros execute exactly 1,000 times. And if you look at the source code, all you see is function foo. You don't actually know if it will be in line and bar or bars at the moment. And you see that there's equal weight to both of the branches. So one has no preference over the other. You wouldn't do hot-cold splitting in this case. So you end up, after inlining of this function, you end up with both A and B being in the body of the function bar or bars. What you really want to have as a result, and what you achieve with the binary level optimization, you actually, in each different case of inlining, you end up with one statement or one macro being as a cold block and the other being in the main hot body of the function. There could be solutions for AutoFDO, how it can be solved, but this is much harder, much more difficult than doing the same sort of optimization at the binary level. So again, I want to thank the community, and I want to say thanks to Rafael Auler, a Facebook intern who helped me a lot with this project, and Gabriel Poesi, who is helping us with debug information at the moment. Thank you all. Yeah, questions, please. Sorry, could you speak a little louder?
Okay. So have you considered doing this optimization in a linker, like LLD, where you have information about all the relocations, all the functions, and in which you wouldn't have to do all the fixing of HHVM and debug information afterwards?
I think it's definitely a possibility. I did think about it, but this is something that we want to use in practice. And the reality is that we have at least 3 major linkers at the moment. We have BFD linker, we have Gold, and we have LLD. You cannot implement it in every single one of them, and you cannot cover all the scenarios. At the moment, we use Gold. I believe in the future we may switch to LLD, but it will take some time. The binary optimizer works with any linker and any compiler. So this was the main idea behind the project.
And that's a proof of work, right? You've done it, it works excellent. Now it's just like implement this in LLD whenever you become stable enough and you have your feature. But you're ready to do all the work or investigation.
That's true. Yeah, since it's the project based on LVM, I imagine it wouldn't be that difficult to move parts of it to LLD if there'll be such an interest. Yeah.
Right, thanks very much for the talk. It's really nice to see someone getting interested in binary optimization, which I was rather passionate about when I was doing compiler work back in the past. So there's some interesting aspects about it. For instance, doing truly global value analysis, even when you don't have access to the source code, which was always a problem in the past, because when you called a function that was opaque to you, then you didn't know what it was doing with the pointers, and you couldn't get the set of targets for that pointer. Global value propagation as well, and a truly global value propagation you can get through the binary. So I'm a bit of a heretic. I consider binary optimization about the only efficient way of optimizing binary code, typically. And IRs are, one hopes will disappear eventually, but
Okay.
but that's probably never going to happen. Did you look at using the dwarf information to get additional metadata about the program? Because the dwarf information is full of useful, juicy tidbits of information.
Yeah, what you mentioned is totally true. Again, we don't want to replace the standard compile optimizations. And we don't want to compete with something like link time optimization, which is basically a whole program optimization where the compiler gets the whole view of the program. And some of the optimizations are better suited for compiler in the whole program mode. We could use potentially some dwarf information to find variables to do alias analysis, but at the moment it's not our goal. We want to do something that compiler cannot, or if it's very difficult for compiler to perform. And for this, I'm not sure how much information, extra information, we can extract from dwarf, especially when we work with functions written in assembly. They typically don't have any debug information embedded.
Yeah, I think it's better to be able to work independently of metadata from the compiler, particularly when you don't have access to the source code of the original code. So inlining in particular was something we identified as a low-hanging fruit. With this.
That's a good point. We'll definitely do inlining, but we'll start with very simple functions. Once you do or more complex inlining, you probably want to do register relocation. And once you enter this space, we actually start to competing with compiler, and I'm not sure what we will gain from this. I would rely on something like LTO and AutoFDO to do inlining of large functions. Yeah.
Yes. So a potential future of this might be to use machine learning to do energy minimization on whole programs, but that's maybe way off in the future. So.
Yeah, that's interesting. I haven't considered that yet, but yeah, thanks.
Information may be helpful when you do data flow analysis, because at least you know Panchenko is a structure with a gradient.
Yeah.
Axis will be linear.
Yeah, exactly. I think, yeah, you're right. Once we start doing the data optimizations, yeah, this will be indeed quite useful. Yeah. Questions? Yes.
Hello? Oh.
Yeah. That's
you mentioned that linking with the GNU link script up the link time to 20 odd minutes.
Yes, 20 minutes what it takes us with the linker script.
I was just wondering if you had looked into the cause of that, because from our experience, most of the time in linking is reading from the disk and then writing back out. The actual link script processing and laying out your sections and symbols is actually mostly free.
It's mostly what?
It mostly comes for free. It's all CPU bound. So I'm kind of surprised that you're experiencing that, and there may be a problem there that...
Yeah, we were much surprised ourselves, and a couple of guys on our team, they looked into this. They found that the algorithm that Gold uses is actually a function of m by n, where m is the number of functions in the input binary, and n is the number of functions in the linker script. And the number of functions that we currently have is about 100,000 in the binary and tens of thousands in the linker script. So this results in these slow linker times. We tried to improve it. We tried to replace some of the lookups with hash table. We improved it a little bit, but we couldn't actually get it to the point where it was working.
Okay. I think you could probably get a lot more out of that. So we did a similar thing recently where we reordered a whole program just by reversing it. So that was 500,000 symbols all defined in a link script. And that took less than a couple of % overhead to the overall link time for a big application.
Mm-hmm. And you were using Gold too?
No, we have a proprietary linker as part of our tool chain.
Oh, okay.
And we actually do a number of these optimizations that you mentioned. So I actually believe it's great that you're doing it on a separate binary, but I also think it would be encouraged to have this also available for the linker to do as well. So you would have the choice of doing it as a post-processing step or doing it at link time, because there are a number of these things that you can do, peephole optimizations, with very little to no overhead. So I would really encourage that as a direction, and don't let the link script stuff put you off, because I'm fairly certain that should be a fixable thing. The other thing I had just an observation talking about emitting the relocations. As you say, we do this as part of the link step, so we see the relocations. You can't rely on the relocations being absolute. As you said, people writing ASM, the symbol information is not always all there and correct. Also, the assembler can do optimizations that if it's within the same section, it doesn't have to emit a relocation because it knows how many bytes to jump. So even if you emit the relocations after a link, you still won't have the complete picture, so you would still need to scan for jumps. So just a heads up on it.
So the relocations coming from the linker will be in addition to what we recreate internally. You're completely right, yeah.
So we've done an effort to make all of those, even calls to locals within the same section, explicit, so relocations are omitted. So if that's something you're interested in, I'd be more than happy to help you out with that.
Okay,
Right.
yeah, thanks. more questions? Thank you. Thank you.